Today we shall learn what are real numbers and we shall discuss some of its properties. We shall define set of real numbers axiomatically. So first let's start with a set of natural numbers. So set of natural numbers consist of numbers 1, 2, 3, 4, so on. Then set of whole numbers. If I add 0 in this set, we get a set of whole numbers. Then set of integers. If we take negative of each number, for example 2 and minus 2, 3 and minus 3, and so on. So this is set of integers. Then set of rational numbers, the numbers which can be written in the form of p over q, where p, q are from this set of integers with condition that q is not equal to 0. So this is set of rational numbers. And finally the set of irrational numbers. So these are those numbers which cannot be written in the form of p over q. So which are not rationals are called irrationals. Then finally set of real numbers, which is the topic of our study. So it will be denoted by R. So real numbers are the numbers, either they are rational numbers or they are not rational numbers. So this is the union of Q and irrational numbers. Either any real number is a rational number or it will be an irrational number. So there is no real which is outside both of these sets. So now let's discuss some axioms which the set R satisfies, and then by using those axioms we shall prove certain properties of the set of real numbers. There are two binary operations defined on R, which are number 1 addition operation, that is, if you take two real numbers x, y in R, we have their sum x plus y in R. So this is addition operation on R. So for any pair x, y from the set of reals, we have x plus y, a third number, in R. Second operation is multiplication operation. For any two numbers x, y belonging to set of reals, we have the product x into y this also lies in R. So this operation xy goes to x into y is called a product operation. So set of real numbers equipped with two binary operations. One operation is addition operation and another is multiplication operations. All real numbers, that is all elements of this set, satisfies certain properties with respect to these two operations. So now I am going to list those properties which are being satisfied by the elements of R with respect to these two operations. So first I will describe properties of addition and then I will describe properties of multiplication. So first is properties of addition. First property is, if you take three real numbers x, y, z from the set of reals, then x plus y plus z is same thing as x plus y plus z. Second is, there exists a number e in R such that x plus e is e plus x is equal to x for all x in R. So there is a number which is called identity. If we add that identity in any real number, the real number doesn't get changed. So we already know that this number e is 0. So x plus 0 is same thing as 0 plus x is equal to x for every real number. So this identity element is unique in the set of real numbers. You can't find two different zeros having this property. So the third one is existence of additive inverse. So in the set of real numbers we have this property: for each x in R there is some y in R such that x plus y is identity, that is x plus y is 0, and this is same thing as y plus x. So y will be called additive inverse of x. Y will be called additive inverse of x, and we shall write y is equal to x inverse. And we already know that what will be this inverse element. This should be minus x. When we add minus x in x, we get answer 0. So this x inverse is minus x. So every element in the set of real numbers has additive inverse. The fourth property is commutativity. So for any two reals x and y, we have x plus y is equal to y plus x. So these are the four properties satisfied by the set of real numbers. The first property which I have said, that addition operation, that property sometimes is called a closure property. Set of real numbers is closed under addition, or there is a binary operation under addition. These two things are synonym. So now we shall discuss the properties of multiplication. The similar kind of properties are satisfied by the set of real numbers with multiplication operations. So properties of multiplications. So one, we already know there is a multiplication binary operation, that is product of two real numbers is again a real number. This property is sometimes called the set of real numbers is closed under the multiplication. So another is if we take three reals x, y, z, then x, y, z is same thing as x into y, z. This is called associative property under multiplication. And in case of addition, the similar property was the associative property under addition. Second is there exists some e dash in R such that x times e dash is equal to e dash times x is equal to x. This number, which is analogous to the identity of addition, is called identity with respect to multiplication. When this number multiply with any real number, the real number doesn't change. So in the same way, when we had some number which we added in real number, the real number was not changing. At that time the additive identity was 0. But here the multiplicative identity is 1. So we have 1 in the set of real numbers having property that x multiplied by 1 or 1 multiplied by x gives us x only. So this number is called multiplicative identity. The third is existence of multiplicative inverse. So for each x belongs to R, for each x belongs to R minus 0. So I'll explain that 0 will not have multiplicative inverse. So take any real number which is non-zero. For each x belongs to R minus 0, there is some y in R minus 0 such that x times y is identity is same as y times x. Such y is called the multiplicative inverse of x. So we already know that here e dash is 1. So it means this y is reciprocal of x. So here in this case y is equal to x inverse is equal to 1 by x. So that's why here we have omitted 0, because 1 over 0 is not defined. So every non-zero number has a reciprocal which we shall call as the multiplicative inverse of that number, and when we multiply the multiplicative inverse with the number we get identity element, identity of multiplication. The fourth similar property is commutativity. If you take two numbers from the set of real numbers, then x into y is same thing as y into x. So these were the properties of multiplication. Now there is a distributive properties. So for any x, y, z in the set of real numbers, we have x into y plus z is equal to x times z plus x times y into plus x times z. So if you have three numbers x, y, z, first you add y and z and multiply with x, or you multiply xy, multiply xz and then add, you will get both the answers same. So the set of real numbers satisfies all these properties, and any other set which satisfies all these properties with respect to these two operations, addition and multiplication, will be called a field. So here we call R is a field, and I said any set which satisfies these properties is also called a field. For example, set of complex numbers, which you have already studied in your +1 classes, also satisfies all these properties. So set of complex numbers is also a field. These were certain properties for which we have not given any proof. The proofs are obvious. Such things whose proof are obvious, or such properties which doesn't require any proof, are called axioms. So these were the axioms for the set of real numbers. Now by using these axioms, we shall prove some more properties of set of real numbers which are based on these axioms. So number 1. Prove that zero times x is equal to 0 for each x in R. So any real number when multiplied by 0, we get the answer 0. So by using our axioms, we shall prove this result. Solution. So first write this 0x plus x is equal to 0x plus 1 times x. So 1 is identity element. Now here I have assumed that 1 times x is x because 1 is multiplicative identity. Now apply distributive property here. So 0 plus 1 times x. Now use the fact that 0 is additive identity. So 0 plus 1 is same number 1. So this is 1 times x. So 1 is multiplicative identity, so it is x. Add additive inverse of x both sides. We get 0x plus x plus minus x is equal to x plus minus x. So this implies, now here use associative property of addition, right? 0x plus x plus minus x is equal to, now x plus its additive inverse gives us identity element, and here also x plus its additive inverse gives identity element which is 0. So I can write here also 0. 0 plus anything is that same number. So 0 times x is now 0. 0 times x is equal to 0. So clearly I have not used anything beyond the axioms which I have described earlier. So by using those axioms only, I have proved that 0 times x is equal to 0. Next we prove that minus 1 times minus 1 is equal to 1. Again, by assuming my axioms, I will prove this result. Solution. So let one plus minus 1 is equal to 0. So I have added additive inverse of 1 in 1. So when I add additive inverse to any number, I get additive identity. This is my definition of additive identity. So this step is true. Now multiply both sides by minus 1 and use distributive property. So we get 1 plus minus 1 into minus 1, and here 0 times minus 1 is 0. This I have just proved that 0 times x is 0. So now by using my previous result, this thing is 0. So here by distributive property 1 into this thing, but 1 is multiplicative identity. So 1 multiplied by minus 1 will not change. So this is minus 1 plus this is minus 1 times minus 1, this is equal to 0. Now add additive inverse of minus 1 both sides, or I can say add 1 both sides. So I get minus 1 plus minus 1 into minus 1 plus 1 is equal to plus 1. Now since the real numbers are commutative, under addition I can bring this product here and take minus 1 here. Now minus 1 is additive inverse of 1. So when 1 will be added in minus 1, this will give me a 0. So minus 1 into minus 1 plus 0 will give me minus 1 into minus 1. So this is minus 1 times minus 1. I have got plus 1 here. So let's move to next property. Now we shall prove that minus of minus x is x. Let y be additive inverse of minus x. This implies minus x plus y is equal to the identity element. This is definition of the additive inverse. So y is additive inverse of minus x. So we have already assumed in our addition axiom that for any real number x, minus x will be its additive inverse. So x has additive inverse minus x. So this is now real number. So its additive inverse is y, but by my axiom, this y must be minus of this thing. So y is equal to minus of minus x. So minus of minus x is additive inverse of this thing. Also, we know additive inverse of x is minus 1, that is x plus minus x is equal to 0. So it means x is additive inverse of minus x. Here we have said that y is additive inverse of minus x. So by uniqueness, this y is same as x. So from these two we get y is equal to x. So if I put x equal to y, here put y equal to x, we get x is equal to minus of minus x. Next, prove minus 1 times x is equal to minus x. Now this minus 1 is additive inverse of 1. 1 is multiplicative identity. So this minus 1, which is additive inverse of 1 when multiplied by any number x, gives us the additive inverse of that number. This we want to show. So now consider one plus minus 1 is equal to 0, because this minus 1 is additive inverse of 1. Therefore by definition of inverse we have this equation. Now multiply both sides by x, we get 1 plus minus 1 times x is equal to 0 times x, which is 0. Now use distributive property, I get 1 times x plus minus 1 times x is equal to 0. So 1 is multiplicative identity, so this is x plus minus 1 times x is equal to 0. Now it means this number has additive inverse this number, but by definition of our additive inverse, if this number is additive inverse of this number or this number is additive inverse of this number, then one will be negative of the other. So if this is additive inverse of this, therefore minus 1 times x will be equal to minus x, because x has additive inverse minus x. So by uniqueness of the additive inverse, we have this number equal to minus x. So let me first prove the uniqueness of additive inverse, because this property I have used so many times. So let's first prove that additive inverse of any real number is unique. Prove that additive inverse of each real number is unique. Let y and y dash be two additive inverses of x. We want to show that y and y dash are same. So let us consider this y is equal to y dash plus x plus y. Now, why this equation is true? Y dash is additive inverse of x. So y dash plus x is 0. 0 plus y is y. So these two things are equal. Now use associative property here. So we get y dash plus x plus y. Now use the fact that y is additive inverse of x. It means y plus x is additive identity, which is 0. So y dash plus 0 is y dash. So we have proved that y equal to y dash if y and y dash are two inverses of x. So in additive inverse is unique. Similarly, you can prove that additive identity is unique, multiplicative identity is unique, and multiplicative inverse is also unique. Now, next result we shall prove that minus x into minus y is equal to xy for any real numbers x and y. We shall use the results which we have just proved. So minus x into minus y, I can write it as this minus x can be written as 1 times x. This I have proved that when I multiply it by additive inverse of identity to any real number x, we shall get additive inverse of x into minus 1 times y. Now since this product is commutative, we can bring this minus 1 here. So minus 1 into minus 1 times x into y. So we have already seen that minus 1 into minus 1 is 1. So this is 1 into x into y. But 1 is multiplicative identity. So this is x into y. So we have proved what we wanted to prove. So these were some of the properties which we have proved. But there are some more properties which we need to prove about real numbers by using our axioms. So we shall do those also step by step.